Been reading some Kolmogorov statistics and the Solmonov induction, and I think it's really interesting to take AI and look at it from this perspective, which is from the sort of technical statistical perspective. Now, people like Kolmogorov and Solmonov, they really didn't specifically create AI as we know it today, but their work is the foundation of AI, in particular Solmonov induction and Kolmogorov statistics. Kolmogorov wrote in the 1930s when he basically formally showed that you can infer conditional probabilities from data. Now that might sound almost obvious today. Duh, yeah, that's what we do. That's what most of AI does. But in the 1930s, that wasn't as obvious as it is today. So you look at stuff and you can get the probability that a certain observation belongs to a particular distribution. So I see a cat, and the probability that what I see is a cat is very high. Like that kind of inference wasn't obvious. In particular, it wasn't formally proven to be true. And that's one of the main observations that Kolmogorov added. Now, in the lecture that I'm discussing here, this is a Kolmogorov lecture by a certain person that I don't even want to go into the details. Links in the show notes. There's a Kolmogorov lecture in one of the UK universities, and they honor the statistician and mathematician, and the lecture is about his work. So in this particular lecture, I think what transpires really well is just this very simple view of what AI actually does. So what AI does is it creates a set of filters by which we can then draw inference from. So we look at data. Let's take LLMs. We look at a massive amount of data, and then we try to learn filters from that data, or masks, or something like that. Like, words are a bit elusive here, but think about it like we're trying to find structure in the data, right? We're trying to find something that, okay, this type of data belongs to this filter, and this type of data belongs to that filter in a very high dimensional Hilbert space. And at inference time, what we're trying to do is then match those filters. So, I see this constellation. I think I need to turn left. So the filter that I'm applying is the one that I need to turn left right now, which is what FSD does. Or this prompt, write me a poem that sounds like Shakespeare. Well, that's a certain filter that is write a poem and then write a Shakespeare. Now, what RL does, it finds the most optimal way in that set of filters. So once we pre-train a model, we have, let's say, a less dimensional, but still very high dimensional set of filters, and RL just gives me the most efficient path towards a solution given a certain prompt. So that's roughly the way we see AI. I think it's useful to think about it that way. Now, the fundamental question, I'm actually at the AI Infra Summit here at Santa Clara, which is all about, infrastructure and hardware. And I would say for years now, hardware infrastructure has been NVIDIA versus the rest of the world. And the rest of the world is trying to A, catch up, B, compete, C, take share, D, get their own maybe dominance, all of that stuff. And I guess one of the things that is important when you will look at the space is you have to be able to predict the future. And in order to predict the future, you have to understand fundamentally what is behind all this AI. And what behind all this AI is a massive amount of linear algebra, in particular the computation of filters based on data, and then the computation of the RL side of things to find the optimal path given a certain prompt, and then at inference time match the given prompt to the actual data that is to the filter. So that's all in the end: inner product multiplication, dot product multiplication, high dimensional matrix multiplication, determinant multiplication. In the lecture, in the Kolmogorov lecture, the professor talks about, for example, 0th order, first order invariance. What that means is that what you want to do, given a certain amount of data, is not just find zero order invariance. So not just, let's say, what 0th order invariance means is that which data is changing my average and which isn't. And the one that isn't is irrelevant for me, so I can kind of discard it. But then there's first order invariance, which is certain data might not change my averages, but it might change my slope. In other words, the position of the data is important, and then you have second order invariance and so on and so forth. So those are very important, I think, additional measures here, and the person actually goes into depth also about the difference between invariance or nth order invariance and features, and there's mathematical difference. But fundamentally, what we're trying to do here is, and this is the main message here, right? We want to stay as general as possible with as much data and as much diverse data as possible. Like, this paradigm is not changing because the math underlying this AI evolution is requiring lots of data in different forms at different dimensions, so we can infer intelligence from it. And the more data we have, the more information we have, because it's not just about 0th order invariance, it's first, second, third, nth order invariance. So positioning of data, positioning relative to the position of others, and I'm pretty sure I'm not even scratching the surface here, but I guess my point is that the more data we have and the more diverse data we have, the more math we can infer from it, and the more intelligence we can draw, and the better we get. And I think that's the reason why fundamentally scaling laws work, why you want to have, what's going on right now with NVIDIA, for example, and it's okay to have competitors, but you want to stay highly general and highly efficient. And what you also want to do, I think, going forward, we have to start thinking about energy. That's another, that's another topic that I want to discuss in a separate discussion. Thank you.